Hello everyone, this is Mr. Porter, and this video will hopefully give you a wee guide through as to what materials and study materials are available for you if you're studying National 5 or higher physics at Larbert High School. So every study material, every thing that we have to help you with your exams and your studying this year is available on the Larbert High website, which, as you can see at the top of my screen there, is larberthigh.com. So if you go to larberthigh.com, Google it or type it straight into the search bar, you'll be presented with this screen here. Now, what I want you to do is go to Departments, Sciences, Physics, and you'll come to this screen here, which has a general overview of physics at Larbert High School, with a wee banner up the top here that has all the courses on it that we offer. So you can see in the middle we have National 5 and higher. That's the ones we're going to focus on. We'll start off with National 5. If you're looking for the higher stuff, then skip a wee bit further on. Right now we're just going to look at National 5. So I click on the National 5 tab. It will explain a little bit at the top what National 5 Physics actually is, the 3 units contained in it, which is electricity and energy, dynamics in space, and waves and radiation. That's this wee green bit here. If we then scroll down a wee bit, the first material we get shown is our National 5 exam preparation checklist and mind maps. So start with the exam preparation checklist. If you just click the wee arrow with the line here, that will download it to your device. Their exam preparation checklist covers everything that is within the course, not just the content we cover, but some general aspects as well that apply to everything you study. So we've got some stuff here talking about using relationship sheets, data sheets, prefixes, again, stuff that applies to every part of the course, not just one individual unit. Talking about significant figures and using your knowledge of physics questions. However, if we keep scrolling down, you'll see that for every topic, it's been broken down for what equations are within that topic at the very start in bold, and then a couple of useful facts as well, talking about some key definitions, units, and numbers. And that goes all the way through, following the same order that you've done topics in class. So starting electricity and energy first, which goes all the way up to electronics, and starting dynamics in space from kinematics all the way through to space. I'm just going to skip through it quite fast now. And then to finish off, waves and radiation, which starts in light and goes all the way down to nuclear physics. So that is a key, it's quite a few pages, 41 pages, but it's a key checklist for everything within the entire course. If we then return back to the National 5 page and we have a look at our next one, which is our mind maps, if I again click on the download button, it'll take me to mind maps again for every individual key area that we've got. Now, these aren't populated, however, they are just there if you need a kind of format to make a mind map for yourself. If we then return again, our top thing, and I would say one of the most important parts of your study website here, are the equation tutorials. Now, there is an equation tutorial for every single equation that you cover at National 5 level. So if we were to scroll down a little bit and I was to pick, for example, number 11, Nat 5 pressure, force and area, that is the equation P equals F divided by A. If I again click on the download button, it'll give me roughly about 10 questions for each tutorial solely on that equation. So if you know there's an equation you're particularly struggling with, it tends to be a lot of time gas laws could be something. So if you're struggling with gas laws, you can go in the gas law tutorial here, and it'll give you, this one only gives you 6 questions because they're a little bit bigger questions. However, there is a tutorial for each equation. Now, it would be a good idea to work through as many of these as possible, because the more you repeat these questions, the better you'll become. If we then scroll further down, that's when we've got all this stuff here. So if we start from the left and work our way across. On the left, you've got your class notes. Now, your teacher may use these in class already, so you may have already seen them. However, if not, this is a second set of notes you can come back to. So we'll just stick with number 1, which is energy conversions, which would have been the first thing you did at the start of the course. If I click on the class notes here, you'll see there are handwritten notes that cover everything within that key area. Now there are examples, worked examples within that the answers are already there, so you can see exactly the type of working you should be doing for questions. However, remember, if you are wanting some practice, it's probably better to use the equation tutorials, because that way you can work through it yourself. Now for each equation, if we look at gravitational potential energy here, in the blue box, it will tell you what the equation is and how it's stated in the equation sheet. Because remember, whenever you do an equation or a calculation, that's what you need to use to start off with. However, you will also get the triangle and all of the rearranged forms. However, remember, and I'm sure your teachers explained this as well, it is always best to write the equation from the formula sheet first before doing a triangle or before doing any rearranged forms, because that's where you get the marks from. The first mark in a calculation is always from writing the equation from the equation sheet. So, if we return back, there are notes for all 14 key areas there. If we then look at question banks here in the middle, now you'll see there's some units that have been split up into A's and B's. So electricity, number 2 is 2A and 2B. That's just to split up some of the different questions you could get asked. But if we again stick with energy conversions, so energy conversions, that 5 questions. Here we get a little bit more exam standard questions. They kind of give you a bit more context. Some of these are taken directly from past papers, whether it be Old National 5 standard grade into, but these give you a bit more contextualised exam standard questions. So once you have really nailed the equation tutorial and you feel as though you have potential energy and know how to calculate potential energy from that equation tutorial, you can move on to the question bank and you can start to see how we can contextualise these a bit more and actually do a little bit more exam standard questions. Now, there's a lot more questions here, and you see the parts A, B, etc. However, as they get on, they will become more and more challenging. So you can, if you feel you need a little bit more of a challenge, you can jump to the later parts of the question bank. If you feel you want a nice easy start, you can start from the top and work all the way through. Now, the good thing with the question banks is, if we again return back, there are answer files. There's not answer files for the tutorials, so if you want the tutorials marked, you need to give them to your teacher. However, question banks, there are answers. Now, they're not full answers, so they don't give you the working for all the calculations, but they will give you the numerical final solutions. So if you want to check your final answer, you can do that. However, make sure you're not just writing that, you're actually doing the full working for each question. Where it's a describe or explain, or a question that doesn't involve a calculation but involves a bit of words or language or something like that, then you can see the full answers there. However, for the calculations, it's just the final answer. So, that's our top bit there. We've got our notes, our question bank, and our answer files. If we then scroll down a bit further, you see we have homeworks on the left-hand side. Now, these homework exercises may or may not be the homeworks that you get assigned in class. Sometimes your teacher may assign a slightly different one, so that then they can use these homeworks. Again, if we look at energy conversions A, they could possibly use these homeworks as even further studying. So again, it's just another way to apply what you've learned, maybe in the question banks or in the tutorials, to a little bit more contextualised questions. So far, we've got 3 different ways for you to practice. You've got your tutorials, your question banks, and the homeworks here. Now, if we then look at past papers here, again, you'll probably have used past papers to quite a big extent already. However, the first things I want you to look at here is the top 2 parts of past papers, where it says data sheet and relationship sheet. Now, they are your absolute saviours. In class, you will probably be given a data sheet and relationship sheet by your teacher most times when you're doing equation work. However, it's important that when you're studying at home, you can also access them. So here we've got your data sheet, single bit of paper, and your relationship sheet. Again, just a single bit of paper. Remember, in every test and exam and prelim and FAB and everything you do, you will always get access to those 2 bits of paper. Always. So it might be beneficial for you at home to print those 2 bits of paper out or save them on your iPad so you've always got them to hand. Then if we scroll down a bit further, we've got numbers 1, 2, 3, where it says electricity energy equations, dynamics in space equations, and waves and radiation equations. So if we stick on the first one, electricity energy equations, this gives you every equation for that whole unit. Similar to what you've got in the equation sheet, and what we've got in the notes as well, the equations are here. So the ones that are highlighted in pink and in the boxes, that is what's in the equation sheet. However, you also get given it as a triangle and all the rearranged forms, and that's for every equation in that whole unit. So again, if you want to learn equations from the unit, you'd come to this. Now you see here, there's some equations that you should never use a triangle for. Remember, a triangle's only there to give it a little bit extra hand if you need it. Some equations that don't allow for it. Excellent, so that's at the very top of past papers. Now, if we then scroll down a wee bit further, you've got specimen Nat 5 paper topics. If we click on that, that gives you, for each question, multiple choice and written, so WR is just written, it tells you for each question what topic it's on, what key area it's on. And that's for the specimen paper. Now, the specimen paper was a paper that was made at the very start of National 5 so that the people that were sitting at the very first year, 2014, as you see there, they had some kind of past paper, even though the course hadn't run before. So that's the specimen paper topics. Now I click on, if I go back to it, question 1, multiple choice is electricity. So I then go to the National 5 specimen paper questions and answers, and I scroll down to question 1. 1 volt is equivalent to, etc. That's definitely an electricity equation. So the two things match up. And for these, we do have answer files as well. So if I go to the written part, so here's question 1 for the written part, question 2, question 3. If we scroll all the way down, the marking scheme's at the very end. So you've got your multiple choice marking scheme and the written marking scheme at the very end of the paper. And that repeats for every year's paper. So topics, questions, answers, etc. And it goes all the way down as well to 2023. At the minute, it'll be updated every year. Finally, on this wee section, we have got Nat 5 revision questions, so even further revision questions for you to practice. So you can see here, for electricity energy, 65 questions, dynamics in space, 70, waves and radiation, also 65. Now, we have got, at the very top, 200 tantalizers question topics. So if I click on that, it'll tell me for each topic what question numbers they're at. So again, energy conversions, on the first document is question 1 to 30. So I return here, and I go to electricity energy questions. I'm just going to view it. So it's a PowerPoint. Oops. Let's go back the way. So we'll review it. So electricity energy tantalizers, question 1, question 2, etc. There's a question on each slide. So you can print them off to use as flashcards or whatever you think might be useful for you. However, there are answer files as well. So there's answer files in the form of PDF. Again, the calculation ones are purely the numbers, not the working. So if you want the working checked, you have to ask your teacher for that. So there's tantalizers for further revision if you need some extra resources, and these are a very good resource to use as well. If we scroll down a wee bit further, we've got proper mind maps here. So we had the mind maps at the start, didn't really have much on them, but these mind maps, we go to the first one, so just for electrical charge, it says everything for charge, an equation, some examples, definition of current, AC, DC, etc. So there are pre-made up mind maps here as well for many different sections. Finally, last two, we have got Kahoot quizzes for each unit as well, or each topic, each key area. If you want the Kahoots, you can see Mr. McMillan's search name is there. You can search that into Kahoot, but you might get a chance to use in class as well. And we also have podcasts for each note and past paper. Now, that means that if you go to Mr. McMillan, you'll need to actually take in a memory stick or something to transfer it across. You can actually get audio of these notes and these past papers being explained to you. So if you're working through a past paper and then you're marking it, you can get Mr. McMillan speaking to you, telling you, right, this is where these marks are coming from for this 2015 paper. So that's a very good resource as well. If you want that, you'll have to go and look that out from either your teacher or Mr. McMillan himself. At the bottom down here, we've got a few final wee bits. You've got the National 5 course specification assignment guide, if you so choose to have a look at them. And finally, how the exam paper and assignment is worked and how the marks get scaled up. So that's everything that is on the website for National 5 Physics. Any questions about that, go and ask your class teacher and they'll be able to help you look at what is actually available and what is best for you in your studying. Right, let's have a look at higher now. Higher, very similar. Again, breaks down the units here. So electricity, particles and waves, and aerodynamic universe. And if we scroll down a wee bit, we've got, again, an exam preparation checklist. So this again includes general aspects and breaks down every little bit of the whole course. So you can look through this and see all the key elements from the whole course. And then you've got some blank mind maps as well, if you so choose to use them. We have got some revision questions or revision exercises at the top here. So I go in the electricity one. We have got lots of extra questions we can ask here. So there's 100 marks in this document. Plenty of marks for you to work through, as well as answers for you to check. And these answers are worked examples, so you can look through exactly where the marking comes from. So they are very, very good questions to work through because they give you the full solutions you can check at home. Now if you scroll down, if you have watched in Nat 5 already, you'll already know this. I'm not going to go into too much detail for the higher because it is quite self-explanatory. However, we have class notes, question banks, answer files here. Class notes is a note for each individual key area within the higher course. It starts off with uncertainties and goes all the way down, as you can see, to Hubble's law and data handling questions. Question banks, well, if we look at uncertainties question bank, you've got plenty questions for uncertainties, looking at different C's of data and finding out different percentage uncertainties, absolute uncertainties, etc. for all these questions here, and you have answer files as well. However, these answer files are just the numerical solutions, not the full worked solutions. Now if we scroll down, we have got higher homework exercises you can work on as well, higher past papers. So again, you've got a data sheet, relationship sheet, and every past paper is broken down with the topics, the questions, and the answers, all the way to 2023. And then you've got more revision questions here as well, where they're split up into topics. So you see the topics here. These are higher 200 toppers questions. And then you've got questions, again, just on a PowerPoint, where you can work through these individual questions in a PowerPoint style with the answers provided too. You've also got higher podcasts. If you, again, want higher podcasts, you'll have to go either to your class teacher or Mr. McMillan, and they'll be able to provide these podcasts. And then you have some mind maps here as well. So here's a semiconductor mind map. If we look at just the electricity ones, there are electricity mind maps for the course as well. You'll need to rotate these. So save them onto your iPad as a PDF and rotate them around. Again, you've also got a course spec, an assignment guide, and information about how the exam and the assignment is marked. So, that is all the materials that are available for National 5 and higher on the Larbert High School website. There are, however, many other websites to use for further revision as well. One off the top of my head that is used quite a lot by a lot of National 5 classes especially is mrsphysics.co.uk, where there's lots of extra notes and questions on that. So if you're looking for that, or if you want some other websites to look at, by all means have a wee chat with your teacher and they'll be able to point you in the way of some other good websites as well. Any other questions about the resources that are available to you for studying National 5 and higher physics, feel free to ask your teacher. Thank you very much. So this worked example is from the 2020 past paper, section 2, and it's going to be question 7. Now this is on electronics and circuit theory. So, we've got a circuit here. A security floodlight is used to automatically illuminate an area outside a building when it gets dark. The circuit for this system is shown below. The resistance of the variable resistor is set to 16.6 kilo ohms. The transistor, in this circuit has a switch-on voltage of 0.7 volts. The light-dependent resistor, the light level decreases to the point where the resistance of the light-dependent resistor is 3.4 kilo ohms. Show by calculation the transistor is switched on at this level. Excuse me. Now, there's a few things in that. Where it says the transistor has a switch-on voltage of 0.7 volts, sometimes in a question they'll tell you that, sometimes it's expected you just know that. For an NPN transistor like we have here, the switch-on voltage is 0.7 volts. Now, there's a lot of information in that diagram, which we will come back to at some points throughout this question. However, right now, what we're going to do is we're going to hop over to our notes. And what you should have recognised from the diagram is it's a voltage divider circuit. Right? There's two resistor-like components, in this case a variable resistor and an LDR, that act as a voltage divider, each sharing the supply voltage, which is 5 volts. So if you have a voltage divider circuit, well, it means you're going to use the Bayer equation. Now, if we're using the Bayer equation, we want to find out a certain voltage. And the voltage we're finding out, V2, in this case, will be the voltage across the light-dependent resistor. Because this bottom voltage, that is telling us whether or not our transistor is switched on or off. If the voltage across the light-dependent resistor is greater than switch-on voltage, which we already talked about, 0.7, then the transistor will turn on. So we want to calculate the voltage across the LDR. So we hop back there. We then need to know, right, what is the resistance of the LDR? And that's going to be our R2. So my R2 up the top is, well, it's 3400. Because we know the resistance of the light-dependent resistor, as it says where it says question A, well, it's 3.4 kilo ohms. 3.4 kilo ohms is just 3,400 ohms. Then that means R1 will be the other one, which is 1660. And R2, we already talked about that. And I've already said the supply voltage is 5 volts, as it shows us here. The supply voltage is 5 volts. Not the 230, ignore that now. The actual supply voltage for this circuit is 5. Then we can calculate it. So V2 will be 0.85. Oh, missed the 5. 0.85. Right? And that's it. You don't actually have to say anything else. But if you wanted to have clarity, you could say, therefore, what's it actually asking for? The transistor switches on. So you would say, therefore, the transistor will switch on as the voltage is greater than the switch on voltage. Perfect answer. Because we calculate the voltage across the LDR to be 0.85, which is bigger than 0.7, and that's a switch on voltage. So that was question 7A. Now if we move on to B, well, actually B part I, the floodlight is connected in part of this circuit is controlled by a relay. Explain why the relay is used. So the relay is this part here. Now, a relay might be something you went over in class already, but a relay coil is just a coil of wire. Now, whenever a current, electrical current flows through that coil of wire, it'll produce a magnetic field. Now that magnetic field, we can see it's been created in that kind of dashed box there. When that magnetic field is created, it'll effectively pull that relay switch towards it and close the switch, letting this second circuit, the right-hand side, operate. Now the reason why we've got the relay switch there, well, it's actually quite obvious. You can see on the left-hand side, this circuit with all the stuff in it, the resistor, the light-dependent resistor, that operates at 5 volts. The floodlight, however, doesn't. The floodlight operates at 230 volts from an AC power supply, usually the mains voltage. UK mains voltage is 230 volts AC. So the answer for this one would just be something along the lines of the control circuit with the LDR operates at 5 volts. The floodlight operates at 230 volts AC. This means the relay allows both circuits to work together. Isn't that nice? You could also say the two different parts of the circuit operate at different voltages, or the floodlight requires a higher current than can be supplied from the transistor circuit on the left. Anything like that is perfectly fine. But it's just looking at, right, these two circuits operate at different voltages. How can we explain that? Why is that happening? Part II. The floodlight has a power rating of 575 watts. Calculate the current of the floodlight when it is switched on. Well, we know that electrical power equals the current times the voltage. They tell us what the power is. You want the current. We already know, and we've already talked about it extensively, that the voltage is 230 AC. So if I rearrange that and calculate, I will just be 2.5 amps, or amperes. Excellent. Part III. The following fuses are available for use with the floodlight. State which of these fuses is most appropriate for use with the floodlight. Well, remember, the general rule is there are two fuses we tend to always favour, and that's the bottom two, 3 amps and 13 amps. So you're probably going to do 1 to 2. The general rule is, we'll go back to our notes here, you would select the 3 amp fuse if the electrical power is less than 700 watts. And you would select the 13 amp fuse if the electrical power is greater than 700 watts. For this question, well, in the last question we said the power is 575, so that means that the fuse would have to be 3 amps. And that's it. Another way to think about it is, well, we calculated the current to be 2.5. If we selected a 2 amp fuse, well, it's going to break because the current naturally will be much bigger than it. So whenever you're picking a fuse value, you want to pick a fuse value that's just a little bit bigger than the standard current. In this case, we calculate the standard current to be 2.5. So if we were to get a fuse that's a little bit bigger, the best option there is 3. Because 5 just that much bigger, 10, 15, just keeps getting bigger. So we want a fuse that's a tiny bit bigger than our actual current. So this is going to be our first worked example for one of the more common but also quite challenging questions that pops up quite a bit at National 5. So we're going to look at vectors. Now, the question I'm going to do, as you can see on the screen, is from the 2015 past paper, section 2, and it's question 7. So we'll go through the word solution in a wee second, but just to see what the question actually is, we have got it here. So again, this is from the 2015 past paper for National 5, and it's question 7. So, a ship of mass 5.0 times 10 to the 6 kilograms leaves a port. Its engine produces a forward force of 8 times 10 to the 3 newtons. That's this force here and this force here. A tugboat pushes against one side of the ship as shown. The tugboat pushes a pushing force of 6.0 times 10 to the 3 newtons. Sorry, that is this force here. The mass is given, but we may use that later on. So we've got our port, our tugboat coming out of port with 6 times 10 to 3 newtons, and our ship going forward with 8 times 10 to 3 newtons. Now, whenever you get a vectors question, it'll always say, or usually it'll always say, by scale drawing or otherwise, determine the size of the resultant force acting on the ship. Now, depending on who your teacher is, you may have went over scale drawings, you may not have. I know that in my classes especially, we don't do scale drawings. However, where it says or otherwise, that's using your maths method, which is Pythagoras, and later on we'll use trigonometry and bearings. However, here you can see it's 2 marks, and it just asks for the size of the resultant force. So it's just asking for the actual magnitude of it, which means we're just going to do Pythagoras. So what I'm going to do is I'm going to hop over back to my notes here, and I'm going to redraw out the diagram very quickly. So we have got the tugboat producing a force down the way of 6.0 times 10 to the 3 newtons. I also have the ship itself producing its engine force this way of 8.0 times 10 to the 3 newtons. Now, the first thing you need to identify here is that both of these vectors are coming nose to nose. The point of the arrow is coming together on both of them, which we need to fix. So what we're going to do is we are going to change our diagram. We will keep our bottom line. I'm just going to drop the 0.0 because 0.0 doesn't really mean much. But what I'm going to do is instead of having my 6 times 10 to 3 newtons on my right hand side, I'm going to move it so it is on this side here. Now what I've got is I've got vectors that are nose to tail, or the top of the arrowhead is hitting the end of the arrowhead on the next arrow. So it's following a distinct path from our starting point, which is here, to our finishing point, which is here. Now, in order to get the resultant force on the ship, we're going to need to get this line here. This red line, that's our resultant force. Right, I'm just going to label that as X for now. So, to get our resultant force, don't get rid of that now. To get our resultant force, we're going to need to do, like I say, our Pythagoras. So, our resultant force is equal to our one side squared plus our other side squared. This is where you need to watch your powers. Don't get them tangled up. I've put in my brackets just to make it a lot easier for me to see and distinguish what we've got. If you prefer to change it to from 6 times 10 to 3, change that to 6,000, or 8 times 10 to 3, change that to 8,000, that's perfectly okay. Then what you're going to do is you need to get this just to be X by itself, or whatever letter you've got. So I'm just going to do square root of everything I've got up here. And when you end up putting this into your calculator, you will get the size of the force to be 10 times 10 to the 3 newtons, or 10,000 newtons. Right? That's absolutely fine. Now, that is all you have to do for question 7 part A, part I. Because it doesn't ask for a direction. It just asks for the size or resultant force. So if you give a direction, an angle or a bearing, whatever, even if it's wrong, they just ignore it in this question. The marking scheme says ignore any direction stated in the answer. So all they care about is this part here. Right, we'll move on to the next one. So we have now found the size of the resultant force acting on the ship. If we then move to our next question, it says determine the direction of the resultant force relative to the 8.0 times 10 to the 3 Newton force. Let's move on to that one. So, if you think back to when you did your directional stuff, one of the things that may have been talked about by your teacher is using something you've hopefully looked at in maths, SOHCAHTOA. However, again, your teacher should have explained that in physics, we don't use these two. We only use our TOA, which, remember, stands for tan theta equals opposite over adjacent. Now, if we go back to our diagram up at the top here, so one on the right, we need to figure out, first things first, what angle are we finding out? Now, there's a couple easy ways to figure out which angle you're finding out. Biggest easy way is it is always going to be the angle that is beside your starting point. So my starting point, I've labelled it as S on my diagram. That's the angle we're finding out because it's the angle beside my starting point. It's not this one because this is 90 degrees, and it's not this one because that's my finishing point. I don't really care about that angle at the minute. What I do care about, let's rub that out. What I do care about is this angle here. So, another easy way to remember it, if you don't remember it's the one by the starting point, is it's also the angle beside the point. So in a triangle there's 3 points. You've got point 1, point 2, point 3. It is the angle beside the point, there's no arrowheads at it. At point 2, there's one arrowhead, this one here. At point 3, there's 2 arrowheads. We've got this one, we've got this one. Point 1, however, there's no arrowheads at all. So that's the angle we're finding out. So if that's the angle we're finding out, the opposite is 8 times 10 to the 3. The adjacent is 6 times 10 to the 3. So, in pretty much every question we do, that's the angle we're going to look at. However, if we jump back to what the question actually asks for, it asks for the direction of the force relative to the 8 times 10 to the 3 Newton force. So how I said that this was the angle I care about, well, it's not in this question, because that is not relative to my 8 times 10 to the 3 Newton force. It's opposite it. In this question, however, we're going to come back to the one that I said earlier on we might look at, which is this one here. So in this one, which is a bit of a tricky move on their part, this is the angle we care about because that's the one that's relative to our 8 times 10 to the 3 newtons. So in this case, our opposite, well, it's not going to be 8 anymore, it's going to be 6. And our adjacent now is going to be 8. So, if we go to our tan theta, that means that tan theta will be 6 times 10 to the 3 over 8 times 10 to the 3. So theta by itself is 10 to the minus 1 of 6 times 10 to the 3 over 8 times 10 to the 3. And if you calculate that, it will be 37 degrees. Now, you don't need to convert it to a bearing in this one, because it doesn't really ask for a bearing. It asks just for an angle relative to a force. When we've got forces, forces can be given in angles, like we've got here. Directions in regards to distances or displacements, well, they need a bearing. So if you've got a distance, so something in meters, or a displacement also in meters, then you'll need a bearing. Here, however, with a force, because we calculated our force to be 10,000 newtons. Forces, we just need it as an angle. Simple as that. You can do it with a scale diagram, however, we're not going to do it with that now. So, if we move on to our next one, which is part A, III, well, this is somewhat related to vectors, but it's going to apply something that you've done in forces as well. So this is calculate the size of the acceleration of the ship. Now, as soon as you've got forces, you should try and recognise that forces and an acceleration, you're going to use this bad boy. F equals m times a. Now, the tricky part here is figuring out what force to pick. Now, the force you're going to pick, well, it's going to be your resultant force you calculated in part A, which is 10 times 10 to the 3. The mass is given in the question. It was the very first thing we talked about. 5 times 10 to the 6 kilograms. The acceleration is what we're finding out. Then when you rearrange all that and calculate it out, you should get 2 times 10 to the minus 3 ms to the minus 2, which is quite small, but that's alright. It's a ship moving out, it's probably not going to be accelerating that fast. Now our last one, which again is not overly focused on vectors, but it still does relate to the question, is we've got a ship out in the open sea, it comes to rest. Now remember, whenever you see rest, that means it's not moving, it's stationary. Explain with the aid of a label diagram why the ship floats. This will be quite a nice, easy one to do. So, still question 7. This one, however, is part B. So it's moving on to a whole new part. Now, if we just very quickly draw what some people may call a boat. There are 3 marks for this. So the first 2 marks come from labelling what the actual forces are on this boat. Now, there's a force acting up and a force acting down. Now, as soon as you see a force acting down the way, you should straight away be thinking, well, that's the weight. The weight or the force of gravity acts down the way. If you say just gravity, that doesn't get the mark. You would either have to say weight or force of gravity. Gravity by itself doesn't get the mark. Up the way, however, we've got a few other options we can pick. You could say buoyancy force. Again, you can't just say buoyancy, you have to say buoyancy force. Or one you might be familiar with, upthrust. You could say force of water on the ship. You could say flotation force. Any of them are perfectly good. However, it's just 1 mark for each of these. It's a 3-mark question though. You've just done the diagram. You've not actually explained why it floats. You've explained the forces, but you've not said why this thing actually floats. Well, that's the key word there. They are balanced. Or you could say they're equal and opposite to each other, but by saying they're balanced, that gets you your last wee mark. So, this question is again from the 2020 past paper, section 2, question 13, as we can see here. So it's 2020 past paper, section 2, question 13, and it's on nuclear physics. So, if we look at the question here, in a nuclear power station, nuclear reactions are used to generate electrical energy. In a nuclear reaction, a uranium nucleus is split by a neutron to produce 2 smaller nuclei, 2 or 3 neutrons, and energy. State the name given to this type of nuclear reaction. Now, you've done two types of nuclear reactions, fusion and fission. In this case, we have fission, because it is splitting up into two smaller atoms, or nuclei. It is actually induced nuclear fission, to give it its proper name. But you would get the mark for just fission. Simple as that. And that was for 13A, part I. Part II, well, following on from that, explain how a single reaction can lead to continuous generations of energy. So how can one reaction lead to more and more and more? So it's 2 marks, so you need to say 2 different things here. First thing you need to say is something along the lines of the neutrons that are produced in the first reaction go on to cause further reactions or to split more nuclei, because it takes 1 free neutron to induce nuclear fission. However, at the end of nuclear fission, we're left with 3 free neutrons. So we get a net gain of 2 extra neutrons. Those 2 neutrons can then go on and split more, which will again produce 2 extras, and so on and so on. But you're always left with the one that you started with in the first place. So from one reaction, you could do 3, then 9, and so on and so on and so on. So that's the first mark. Second mark would be then to say this repeats, or this process repeats, and causes a chain reaction. So it just goes on and on and on and on and on. Excellent. So, if we move on to the next one, which is 13B, the waste products from nuclear power stations are radioactive and need to be stored until their activity reaches a safe level. One type of waste has a half-life of 32 years. Determine the time taken for the activity of this waste to decrease to 1/8 of its original value. Now, your teacher may do it in a slightly different way, but if we imagine whatever we start off with being our total, our original total. So we've got part B. We've got all of our nuclear waste at the start. Now, it takes 36 years. 36, sorry. 32, sorry. 32 years in order for it to half itself. So if we start with however much, I'm just going to label it as X now. After 32 years, well, it's going to reach half of that. Then after a further 32 years, well, it halves again, which becomes a quarter. And a further 32 years, it halves again, and that becomes an eighth. And that's where we want to be. We want to be able to half it until it gets to 1/8 of where it started at the beginning. So, see if you show any evidence of halving, you get your first mark. So we've shown evidence that we've halved each time, we get our first mark there. Now, your second mark comes from saying, right, we have 3 half-lives here, because it's halved itself once, twice, 3 times. So 3 half-lives. 3 half-lives, well, it's just going to equal 1 half-life, which is 32 years, multiplied by 3, which will get you 96 years. So it'll take 96 years in order for it to reach 1/8 of its value. However, the key thing you need to watch out for here is watch out for these units. Remember what units you're doing them in. Don't assume it's in seconds or minutes or hours or years or days or months. make sure you're checking. It must be consistent. Excellent. So let's move on to question C, part I. During a typical shift, a worker handling radioactive material received an absorbed dose of 2.2 micrograys from slow neutrons and 3.4 micrograys from gamma radiation. Determine the total equivalent dose received by the worker during a typical shift. Well, first things first, equivalent dose. That is this equation here. H equals D omega R. You get 1 mark for that. 1 mark for that. Now, it's 4 marks for this question, and this is where the marking becomes a wee bit iffy. You've been given both for slow neutrons and gamma radiation. That means you need to figure out each of them. So let's start for slow neutrons first. We'll do gammas after. For slow neutrons, they tell you what the value of D is. 2.2 times 10 to the minus 6. Oh, sorry about that. 2.2 times 10 to the minus 6. And apologies for having to cut that off there. So it is 2.2 times 10 to the minus 6, because in the question it says it's in micrograys. Remember, micro, with the wee kind of funky U, it looks like this. That means minus 6. So, omega R, the radiation weighting factor for slow neutrons from the data sheet, is just 3. Then if you calculate that out, you would get the value H to be 6.6 times 10 to the minus 6 sieverts. That's for slow neutrons. You're going to do the same for gamma radiation. H equals, this time it was 3.4 times 10 to the minus 6 micro. But for gamma, the radiation weighting factor, well, it's just 1. So H is just going to be 3.4 times 10 to the minus 6 sieverts. So you've now found out the individual values for H for both slow neutrons and gamma. But that's not what they asked for. They asked for the total value. So H total, well, it's just going to be the two of them added together. So 6.6 times 10 to the minus 6 plus 3.4 times 10 to the minus 6. You should get a value of 1.0, or just 1, times 10 to the minus 5 sieverts. Please watch out, and the stuff in green I don't want you to write, don't write it as that. Because the value before your scientific notation must always be less than 10. So that's why we've changed it in the way we have. And that's that. Final one. I believe it's the final one. Yep. So part C, II. Oh, help if I select the pen. Well, it's asking for, well, it tells you the annual dose limit for a radiation worker is 20 millisieverts. The M means milli. Determine the number of typical shifts it would take for the worker to receive a dose of 20 millisieverts. So if you're wanting the number of shifts it's going to take, let's say number of shifts is just N. You know the total they can receive, so that's the maximum they can receive, and you know how much to receive in one shift because you just calculated that. So that's just lifted from our last question. So you've got the total they can receive divided by the number they receive in one event, which means we can calculate how many shifts they can have in total before they reach their maximum, which would just be 2,000 shifts. And that's a nice easy one to wrap up with as well. Excellent.